This is a quick recap video of chapter Work, Energy and Power. So let's start with work. Work is said to be done whenever a force acts on a body and the body moves through some distance in direction of the force. If the force F makes an angle theta with the direction of displacement S, then the work done is W will be equals to F dot S, or this will be equals to Fs cos theta. Now work done is a scalar quantity. It can be positive or negative depending on the theta is acute or obtuse. The work done by friction or viscous force on a moving body is negative. Work done is a scalar quantity. Now first, when if theta is equals to 0 degree, then W will be Fs. Work done is maximum. And second case, when theta will be equals to 90 degree, then work done will be equals to 0. Work done is now 0. And now let's understand work done against a variable force. The work done by a variable force F in changing the displacement from S1 to S2 will be equals to integration F dot ds limit from S1 to S2, which will be equals to area under the force displacement curve. Now units of work. The SI unit of work is joule. 1 joule of work is said to be done when a force of 1 Newton displaces a body through a distance of 1 meter in its own direction. 1 joule will be equals to 1 Newton into 1 meter. And now second thing is that the CGS unit is erg. 1 erg of work is said to be done if a force of 1 dyne displaces a body through a distance of 1 centimeter in its own direction. 1 erg will be equals to 10 to the power 7. 1 joule will be equals to 10 to the power 7 erg. Now work done in terms of rectangular components. F is equals to fxi cap plus fyj cap plus fzk cap, and S is equals to sxi cap plus syj cap and szk cap. Then W will be equals to fx sx plus fy sy plus fz sz. Now Newton's third law and work done. F12 will plus F21 will be equals to 0. For two bodies, the sum of the mutual forces extended between the two bodies is 0 from Newton's third law. But the sum of the work done by the two forces need not always cancel, i.e. work done 1 2 plus work done 2 1 cannot be is not is equals to 0. However, it may sometimes be true. Now energy. It is defined as the ability of a body to do work. It is measured by the amount of work that a body can do. It is a scalar quantity. Like the work SI unit of energy is also joule and CGS unit is erg. The unit of energy used at the atomic level is electron volt. 1 electron volt is equals to 1.6 into 10 to the power minus 19 joule. 1 kilo electron volt will be equals to 1.6 into 10 to the power minus 16 joule. 1 mega electron volt will be equals to 1.6 into 10 to the power minus 3 joule. Now kinetic energy. It is the energy possessed by a body by the virtue of its motion. The kinetic energy of a body of mass m moving with speed v is k will be equals to 1 by 2 mv square, which will be equals to p square upon 2m. Now work energy theorem. The work done by the net force acting on a body is equal to the change in kinetic energy of the body. W will be equals to change in kinetic energy, which will be equals to half mv square minus half mu square. Now next is potential energy. It is the energy possessed by a body by virtue of its position in a field or configuration, shape or size. For a conservative force in one dimension, the potential energy function ux may be defined as fx is equals to minus du x upon dx, and del u will be equals to uf minus ui, which will be equals to negative integration of fx dx, and limit is xi to xf. Now gravitational potential energy. It is the energy possessed by a body by the virtue of its position above the surface of the earth. The gravitational potential energy of a body of mass m at a height h above the earth's surface is U will be equals to mgh. Now, potential energy of a spring. According to the Hooke's law, when a spring is stretched through a distance x, the restoring force set up in the spring due to its elasticity in such that F is directly proportional to x, or F will be equals to minus kx, where k is the force constant of the spring. It is the restoring force set up in the spring per unit extension. Its unit is Newton per meter. The work done in stretching the spring through distance x will be W will be equals to 0 to x, kx dx will be equals to 1 by 2 kx square. This work done is stored as a potential energy U of the spring. U will be equals to half kx square. Now, conservative force. A force is conservative. First, if the work done by the force in displacing a particle from one point to another point is independent of the path followed by the particle. And second, if the work done by the force in moving a particle around any closed path is zero. Gravitational force, electrostatic force, and elastic force of a spring all are conservative forces. Now, second is non-conservative force. If the amount of work done in moving an object against a force from one point to another depends on the path along which the body moves, then such a force is called a non-conservative force. Forces of friction and viscosity are non-conservative forces. Now, mass energy equivalence. According to the Einstein, mass can be converted into energy and energy can be converted into mass. A mass m is equivalent to the energy E. This relation is given by E will be equals to mc square, where c is the speed of light in vacuum, and we know that c is equals to 3 into 10 to the power 8 meter per second. Now, second, power. It is the rate of doing work. It is a scalar quantity. Power will be equals to work upon time, and this is the formula. Power will be equals to W upon T. Instantaneous power is given by P will be equals to dW upon dt, and replacing W with F dot S, we get this expression, and further we solve this F dot V, and this can by removing dot product we use cos theta, so power will be equals to FV cos theta. Now, if theta will be equals to 0, then P will be FV. Now, units of power. The SI unit of power is watt. 1 watt is equals to 1 joule upon 1 second here. And the larger units of power are kilowatt and horsepower. 1 kilowatt is equals to 1000 watt. 1 horsepower is equals to 746 watt. Now, kilowatt hour. It is the commercial unit of electrical energy. 1 kilowatt hour is the electrical energy consumed by an appliance of 1000 watt in 1 hour. 1 kilowatt hour is equals to 3.6 into 10 to the power 6 joule. Our next topic is laws of conservation of energy. Law of conservation of energy. It states that energy can neither be created nor be destroyed. It can be only transformed from one form to another form. Now, collision. A collision between two bodies is said to occur if either they physically collide against each other, or the path of the motion of one body is influenced by the other. Now, elastic collision. If there is no loss of kinetic energy during a collision, it is called elastic collision. Inelastic collision. If there is a loss of kinetic energy during a collision, it is called an inelastic collision. Linear momentum is conserved both in elastic and inelastic collisions. Now, perfectly inelastic collision. It is the collision in which two bodies stick together after the collision. Now, this is head-on collision or one-dimensional collision. It is a collision in which the colliding bodies move along the same straight line path before and after the collision. Now, oblique collision. if the two bodies do not move along the same straight line path before and after the collision is said to be oblique collision. Now, velocity in one-dimensional elastic collision. Suppose two bodies of mass m1 and m2 moving with velocities u1 and u2, where u1 is greater than u2 in the same direction, suffer head-on elastic collision. Let v1 and v2 be their velocities after the collision. In this diagram, you can see this. This is m1, object of mass m1. This is object of mass m2. This is before collision u1 velocity, and m2 is moving with u2 velocity. And after collision, m1 starts moving with v1 velocity and m2 starts moving with v2 velocity. Now, by the law of conservation of momentum, we can say m1 u1 plus m2 u2 is equals to m1 v1 plus m2 v2. As kinetic energy is conserved in elastic collision, so we can say half m1 u1 square plus half m2 u2 square is equals to half m1 v1 square plus half m2 v2 square. By solving the above equations, it can be shown that in an elastic collision, velocity of approach will be equals to velocity of separation. This is velocity of approach and this is velocity of separation. u1 minus u2 will be equals to v1 minus v2. Also, v1 will be equals to m1 minus m2 upon m1 plus m2 into u1 plus 2 m1 upon m1 plus m2 into u2. And v2, similarly we can write v2 2 m1 upon m1 plus m2 into u1 plus m2 minus m1 upon m1 plus m2 into u2. Now the last topic is coefficient of restitution. The coefficient of restitution for a collision between two bodies is the ratio of the magnitude of their relative velocity after the collision to the magnitude of their relative velocity before collision. So we can write this coefficient of restitution E will be equals to minus v1 minus v2 upon u1 minus u2, and in we put modulus here, and for a perfectly elastic collision E will be equals to 1 for perfectly elastic collision. For a perfectly inelastic collision, E will be equals to 0. Hence, E remains between 0 and 1. For a ball rebounding from a floor, E will be equals to V by U, where U and V are the magnitude of the velocity of the ball before and after the collision respectively. Thank you.